Hello, my name is Kratika Arya and today we'll learn about deadlocks. Imagine a scenario where each car at an intersection is waiting for another to move, creating a gridlock. This is exactly how deadlocks occur in computing. But what exactly is a deadlock? A deadlock is a situation where a set of processes is blocked because each process holds a resource and waits for another resource acquired by another process. For a deadlock to occur, four conditions must be true simultaneously. First, mutual exclusion, where at least one resource is held in a non-shareable mode. Second, hold and wait, where processes holding resources are also waiting to acquire additional resources held by other processes. Third, no preemption, where resources cannot be forcibly taken away from processes and must be released voluntarily. And last, circular wait, where a circular chain of processes exists with each process holding at least one resource that the next process in the chain needs. This condition creates a situation where processes are stuck waiting for each other, preventing any progress. Now let's understand deadlock with an example. Suppose there are two processes P1 and P2 and two resources A and B. Process P1 locks resource A and then waits for 1000 milliseconds before attempting to lock resource B. Meanwhile, process P2 locks resource B and waits for 1000 milliseconds before attempting to lock resource A. This creates a circular dependency, that is, process P1 is holding resource A and waiting for resource B, while processor P2 is holding resource B and waiting for resource A. Neither process can proceed because each is waiting for the other to release a resource, resulting in a deadlock. This situation highlights the mutual dependency that prevents both processes from moving forward. However, deadlock can be detected and prevented from occurring. One such method is Banker's algorithm. The Banker's algorithm is a resource allocation and deadlock avoidance algorithm used in operating systems, named because it simulates a banking system where customers request to withdraw money. Similarly, the Banker's algorithm ensures that a system can allocate resources to each process in a way that avoids deadlock. The algorithm works by evaluating each resource request to determine if it can be safely granted without leading to an unsafe state. It checks whether the system will still have enough resources to satisfy the maximum future request of all processes. If the request can be granted while still ensuring that every process can eventually get the resource it needs to complete, the request is approved. Otherwise, it is deferred until it is safe to allocate the resources. This way, the banker's algorithm dynamically avoids deadlock by only allowing resource allocations that maintain system safety. Now let's explore the different methods for handling deadlocks, which includes deadlock prevention or avoidance, deadlock recovery, and deadlock ignorance. Deadlock prevention involves designing the system in such a way that one or more of the necessary conditions for deadlock are never met. For instance, by ensuring that resources are always shared or by requiring processes to request all needed resources at once. Deadlock avoidance, on the other hand, involves dynamically examining the resource allocation state to ensure that a circular wait condition does not occur. This is often achieved using algorithms like the banker's algorithm. By carefully analyzing and controlling how resources are allocated, deadlock avoidance ensures that the system never enters a state where deadlock is possible. If deadlock prevention or avoidance is not applied to the software, then we can handle this by deadlock detection and recovery. There are several deadlock recovery techniques. First, manual intervention. This method involves system administrators manually identifying and resolving deadlocks. They do this by freeing up resources or restarting the processes that are causing the deadlock. Second, automatic recovery. In this approach, the operating system is programmed to automatically detect and resolve deadlocks. It uses predefined strategies to handle deadlocks without the need for human intervention. The system continuously monitors for deadlocks and takes action when one is detected. Third, process termination. This method involves terminating one or more of the processes involved in the deadlock. The goal is to break the cycle of resource dependency. The system may terminate a single process or all processes that are part of the deadlock to release the resources and allow other processes to proceed. And last, resource preemption. In this method, resources are forcibly taken from some processes and reallocated to others to resolve the deadlock. This may involve rolling back some operations to free up resources. The preempted processes might be paused or restarted once the necessary resources become available. Now let's see the last deadlock handling method, that is deadlock ignorance. It is a simple approach where the operating system does nothing to detect or prevent deadlocks. It assumes that deadlocks are rare and won't cause significant problems. If a deadlock occurs, it is up to the users or administrators to notice and fix it, usually by starting the system or terminating some processes. This strategy is often used because implementing deadlock handling mechanisms can be complex and resource intensive. This is commonly used in many real world systems, including most versions of Unix. Having discussed deadlock handling techniques, let's now delve into their significant impacts on computer systems. Deadlocks in computer systems have several detrimental impacts. Firstly, they hinder resource utilization by causing processes to hold resources indefinitely while waiting for others, thereby reducing system efficiency and throughput. Secondly, deadlocks can destabilize system, potentially leading to crashes or freezes, resulting in downtime and risking data loss. From a user perspective, deadlocks cause applications to hang or become unresponsive, directly impacting productivity, and user satisfaction. Debugging deadlocks is notoriously complex due to their intermittent nature and intricate process interactions, often requiring significant time and effort to resolve. Frequent occurrences of deadlock also signify underlying design flaws in software systems, such as inadequate resource allocation or flawed synchronization mechanisms, necessitating extensive system redesigns. In critical real-time systems like aerospace or medical devices, deadlocks can have severe consequences, including missed deadlines and compromised safety. And there you have it. Everything you need to know about deadlocks in computer systems, from understanding what causes them to exploring how we can manage and prevent them. We have covered a lot of ground. Thanks for watching.